So hi everyone, thank you for joining in person and on Zoom. And today we have a great pleasure of having Rebecca Lewis, who's going to present her work on inference and high-dimensional logistic regression models with separated data.
Thanks. So thank you all for coming. So as Antonin said, I'm going to be looking at inference in high-dimensional logistic regression models with separated data. And this is some work that I've been doing during my PhD with my supervisor, Heather, faculty at Imperial. And if you have any questions, just interrupt and let me know, or if I can clarify anything as I'm going along. So we're going to assume we've got a situation where we've got response variables, y1 through to yn, that are going to be realizations from a logistic regression model. So they take the value 1 with that probability, and they take the value -1 with 1 minus that probability. And we're going to assume this probability depends on some unknown parameter beta star within the p dimensions. And then we've got covariates x1 through to xn. Now, typically, we perform inference on beta star using maximum likelihood estimation. However, this can lead to some problems. So first, there are settings when the MLE does not exist. And this happens whenever you can perfectly separate the data. So all this means is whenever there exists some x of beta, where xi transpose beta is non-negative, you get data separation and the MLE does not exist. So if you look at the figure on the slides, these are just two examples of a case where the MLE exists and the MLE does not exist. And what I've done is I've plotted the values of two covariates against each other and colored the points by the value of the response, yi. And if you look at the left one, what you can see is that no linear combination of the covariates separates the blue points from the red points. So this is data not separated and the MLE exists. Whereas if you're in the right case and you've got this separation based on a linear combination of the covariates, then the MLE does not exist and we call this separated data. Yeah, so what happens is if you increase the magnitude of the entries of any parameter beta that we use, then what you get is you can always increase those entries and you can always increase the log likelihood, so no maximum. Yeah. So another issue is that even when the MLE exists, it can be quite heavily biased when the dimension P is relatively large compared to N. So that's high dimensional settings where P and N both go to infinity. So what we're going to do is we're going to develop inference on beta star that covers these two settings. So there has been some work along these lines. The first of which is probably Sir and Candace in 2019, who developed a new maximum likelihood theory for logistic regression models when P and N go to infinity, so in a high dimensional setting. And what they did is they characterized the bias of the MLE, they looked at its standard error, and they looked at the distribution of the likelihood ratio test, and they showed that the classical results don't apply. And this work was extended by Zhao et al. In 2020 to more general cases. And based on this, Sir and Candace proposed this probe frontier method as a way to correct the MLE, so to remove its bias in high dimensional settings, so that you could obtain a consistent estimator of beta star. So that was our logistic regression parameter. Unfortunately, probe frontier is quite slow. So Logistic et al. Developed this alternative, SLE, that could be used instead, which is a little bit less computationally intensive. The problem with both of these methods is they still require the MLE to exist. So they don't work when the MLE doesn't exist. So along slightly different lines, Candace and Sir also looked at characterizing when the MLE exists. And they did this by expressing whether or not the MLE exists with high probability in terms of a signal strength and also in terms of the relative dimension P over N. So P was the number of covariates, N is the number of observations. And what they showed is that as P grows relative to N, it becomes more unlikely that the MLE exists. Yeah. So for cases where the MLE doesn't exist, there's been a bunch of work regarding penalized logistic regression, which produces an estimate instead of the unknown logistic regression parameter. And I've given some references there. But the problem with this is, whilst it's quite good at producing accurate predictions or, say, accurate estimate of the whole entry of the logistic regression parameter, it's not very good at estimating the individual entries of the logistic regression parameter. So if you wanted to perform something like variable selection, it can be quite difficult to do this using penalized logistic regression. P, dimension of beta star. So yeah, so penalized logistic regression tends to produce biased estimates. And there has been some work that aims to correct this bias. So it aims to do variable selection in high-dimensional logistic regression models. The problem with these is that they assume the sparsity on the inverse precision, so inverse covariance matrix, the precision matrix. And this is something that you kind of want to avoid in practice, as it's not very realistic. So what we've done is we've developed a consistent and asymptotically normally distributed estimator of the entries of beta star. So that was our parameter, our unknown parameter. And the results are valid in the high dimensional setting, where P and N go to infinity, even when the MLE does not exist. And we make no restrictive assumption on this precision matrix. So we don't assume any sparsity on the precision matrix. So how do we do this? So we started by looking at the behavior of the least squares estimator. So we're going to call this beta hat naught throughout. And we're going to look at how this estimator behaves when your response are observations from a logistic regression model. Our motivation for doing this is the fact that the normal theory linear model and the logistic regression model, so the normal generalized linear model and the logistic regression model, they share the same sufficient statistic X transpose Y, and obviously X transpose Y is very closely related to the least squares estimator. Right, so studying the least squares estimator in a binary setting, so with binary outcomes, is not new. Cox and Warmuth, as well as Heather, my supervisor, and her co-authors, they studied what they called the linear improbability model, where instead of modeling the responses, instead of having the probability that Y equals 1 involving the exponential of xi transpose beta, they assume that this probability is linearly related to some unknown parameter, and they suggest estimating that unknown parameter using least squares. So in a way, it's somewhat similar to our method. The only difference is they assume that this is the generating process, whereas we assume that the data comes from a logistic regression model. And the reason ours is slightly more convenient is the fact that this model implicitly assumes this relationship here, that X transpose beta naught is less than or equal to 1 in magnitude, which is difficult. So like you can't guarantee it for all covariates X. So yeah, so ours is similar ideas, but different, a different model, basically. In that case, yes. I call it beta naught because it's not our beta star. Right, so if you look, yeah, that was our model where beta star was unknown. And they take this model. So they're not really related in any way. They're just both using least squares to estimate these parameters.
What's this?
The unknown parameter. So
the probability could be 5, and that's why you have.
That's why we've got that. So it's a little bit awkward, but if you look at their papers, they suggest that in practice, if you were to use what they do is they take away in observations X, then this probability becomes larger than 1, and they remove this to estimate the unknown quantity, and it tends to work quite well. But obviously, in terms of interpretation of the model, it's a little bit uncomfortable, I'd say. Yeah. So if we start with the least squares estimator, beta hat naught, if you look at it under the logistic regression framework, you can see that it converges to what we're going to call beta naught, that's given by this expression. So if you'll recall, beta star is the unknown logistic regression parameter. So we've got a relationship between the limiting value of the least squares estimator and the logistic regression parameter. And here where I say tan h of a vector, all I mean is tan h of the entries of that vector. So this, yeah, sorry. Yeah, fixed design. Yeah. So if this relationship were invertible, you could potentially estimate beta naught using these squares, invert that relationship, and obtain an estimator of beta star. Right? But, I mean, as long as f of this function is well behaved, in practice, that's quite often done. The problem is this function is not invertible. So we've got to do something else. So what we do is we take our vector tan h of x beta star over 2, and we express it in terms of 3 orthogonal components. Right? So all I've done is I've taken the vector in R to the n and expressed it in 3 orthogonal components So these are going to be projections of a vector onto 3 orthogonal subspaces. Okay? So the first term is just the projection onto the line x beta star. The second term is the projection of that vector onto the space orthogonal to the column span of x. And then delta is just going to be the remaining orthogonal component. Yeah, so there's nothing fancy there. I've just expressed the vector in terms of 3 orthogonal components. And I've given the expressions for C and delta on the slide. Once we do this, you can see that the limiting value of the least squares estimator, beta naught, is a linear combination, a linear function of the unknown parameter beta star and an error term small delta. Right? So C and delta were known, but this follows just by applying x transpose x inverse x transpose to this expression. Yeah. So if C and delta were known, this is an extremely easy relationship to invert. So we could potentially convert a least squares estimator into an estimator of beta star, right? So unfortunately, C and delta are not known. But if you look at their expressions, what you notice is that they depend on the unknown parameter beta star only through this term x beta star. Yeah? And what we mentioned a couple of slides ago is that something like a penalized logistic regression is quite good at estimating x beta star when it doesn't estimate the individual entries of beta star very well. Right? So it can get confused about the estimated values within beta star, but overall, in terms of the predicted values, it works quite well. So all we suggest is that you estimate C and delta using something like a penalized logistic regression, where you plug in an estimate of x beta star, and you use that to estimate C and delta down here. You estimate beta naught using the least squares estimator, and then you invert that relationship, and what you get is an estimator of beta star. Yeah?
You say that that's big there.
Yeah. Estimate beta naught using least squares.
So that's the previous method. Beta naught is there.
No.
Oh,
Okay,
sorry.
fine. That was bad notation.
Oh, sorry.
So in both cases, beta naught is the limiting value of the least squares estimator. However, in our case, it's the limiting value under the logistic regression model. In their case, it's the limiting value under the linear improbability model. Okay, so the beta naught is just this expression up here. Yeah, so it's just the limiting value of the least squares estimator. If you take least squares and take n to infinity, what you get is something close to that.
And then what's beta naught hat?
Beta naught hat is least squares. X transpose x inverse, x transpose y. Yeah, and then C and delta, we're going to estimate them using these expressions, where we plug in an estimate of x beta star, say obtained from optimized logistic regression or something.
That's a good question.
Let me show you on the next. Maybe if I.
Can you explain again your decomposition?
So, if you take a vector in R to the n, you can always express it as a sum of orthogonal components, right? So if you decide you've got 3 orthogonal subspaces, you can always project it onto those 3 spaces, and you can express any vector in R to the n as a sum of those sums. That's what I've done. I've expressed it as this sum, which is going to be a projection onto a line x beta star. Then you look at U, which is going to be orthogonal to the column span of x. Yeah, so you've got the column span of x is going to be some space in R to the p. And you look at everything orthogonal to that. Yeah, and then delta. Exactly. Yeah, and then delta, capital delta, is just going to be the remaining term. So if you actually want it explicitly, it's going to be this vector projected onto the column span of x, but not the component that's parallel to x beta star.
But we have a closed form for delta.
Yeah,
It looks a bit like U.
yeah. U doesn't really matter because the minute I take x transpose U, I get to yeah. So it's really just the C, x beta star, and the capital delta that are going to appear down here. Is that okay? Or
I think could you repeat one more time? So we have this beta 0, and then you said how we estimate it.
beta naught is the limiting value of the least squares estimator.
Least squares estimator. No,
least squares is always minimize y minus x beta. So it's always going to be,
And y is like 1 or minus 1.
Yeah.
Okay.
so least squares is always going to be that. Yeah. So we estimate these naught using least squares. Estimate delta by looking at these expressions and plugging in an estimate of x beta star. Yeah. And then you just invert. Right? So the reason we can find an estimate of x beta star is because x beta star is relatively easy to estimate, even when the entries of beta star are not easy to estimate. So for example, say you've got highly correlated covariates, estimating beta star is difficult because typically you get quite confused about which, if you've got highly correlated covariates, they become identical, essentially. Yeah. But even if they're identical, we can still estimate x beta star quite well.
So C and delta is just like,
Yeah. Exactly. Yeah,
and then you probably
approximately, but yeah, you get an estimate of beta star. Yeah. So just to be a little bit more specific, we're going to see beta hat is our estimator of x beta star, and we're going to call x beta star beta. Yeah. Then we're going to define c hat and delta hat to be those things, those quantities there, where all I've taken is the expressions for c and delta on the previous slide and plugged in eta hat wherever eta appeared. And then we're going to let beta tilde star be our estimator. So that's going to estimate beta star. And all I've done is I've inverted that linear relationship and I've estimated the quantity c, beta naught, and delta. Okay. Okay. So that's our estimator. And now we can look at how it behaves. So the first result, which was our original aim, looks at the consistency and asymptotic normality of the individual entries of our vector. So what it says is that beta tilde star, which is our estimator, it says that if you take appropriate choices of alpha, so don't worry too much about that, except taking alpha as one of the standard basis vectors works fine. Right, so you can think of alpha as just picking out one of the entries of our vector. And if you take alpha transpose beta tilde star, our estimator, minus beta star, the true value, what you get is an asymptotically normally distributed statistic that's centered and it has this standard deviation. Right. So this is good. We've got unbiasedness, well, asymptotic unbiasedness of our estimator. And if this standard deviation decays to 0, you also have consistency. And luckily, we showed in the paper that for many randomly generated design matrices X, you can show that that denominator does decay to 0 with probability converging to 1. So it's good. We've got consistency. We can go a little bit further, and given that we've got our asymptotic distribution, we can test whether individual entries of our vector are equal to 0 or not. And to do this, we just use these statistics TI, where we take our vector, our estimator, and we estimate its standard deviation. Where again, to estimate the standard deviation, all you do is you take the expression for the true standard deviation and replace any mention of eta by eta hat. Right, so exactly the same way as before, we can estimate C by plugging in an estimate of eta hat. And you can just do this as matrix gamma, which depends on the variances of the response. So they only depend on eta. You just plug in eta hat again.
the intuition to just like why would you this one? Like first the beta I corresponds to this feature, and we tested this feature as
Exactly. Yeah. Yeah. So the idea is if you put this to, I suppose, lots of features, and you could apply, say, something like the Baroni correction, I suppose, you'd get a control on the full system, something like that. I suppose you could do that if you want to press all of them.
so you can do that for
Exactly. So that was our aim. To essentially say something about the individual entries of the parameter vector, right? I think it's root n. So if you assume the justification for it being root n is that this term is bounded by the eigenvalues of x transpose x inverse. And if you assume that converges, that divided by n converges, then what you've got is an extra root n. Right? So this is going to be the square root of the eigenvalues of x transpose x inverse, roughly. And when that converges, you get root n. Okay. So we can also look at composite estimation error. So if you take the difference between our estimator and the true value in L2 norm, and we rescaled it by root p because this is a vector in p dimensions, and p might go to infinity as well. What you get is you get consistency as long as you've got this assumption on the unknown parameter. And this, for example, would hold if beta star is sparse, which is quite often assumed. So if it has only a small number of non-zero entries, you would have this, or you even have something stronger than that. And then as long as you assume that the eigenvalues of the sample covariance matrix are bounded, which is quite right. So we've got consistency in that sense as well. So whilst that wasn't our original aim, it's good. Yeah, go. Yeah, for
Does it mean that the ratio is first the constant is smaller than 1, or it's expected to have?
So okay, obviously when p is closer to n, it works well. It doesn't work quite as like it gets worse. The smaller p, the better it works, because the smaller p is, the better OLS works, the least squares works. But if you look at this result holds irrespective of what size p is. All it needs is p less than n so that you get existence of the least squares estimator, because you're inverting x transpose x, so you need p less than n. But in terms of consistency for this here, what we did to show that it was consistent for many randomly generated design matrices is we assumed that the eigenvalues of the sample covariance matrix converge. And if you look at the results in random matrix theory, they typically assume P over N converges to a constant kappa. So for that case, you would want convergence to a constant. Yeah.
So the first term, the first condition.
Yeah, this one.
So yeah, this one is, so this is the sparsity.
It's weaker than sparsity though. Yeah.
Some detail.
Yeah.
And the second term.
It just means that you're not. So when you get the eigenvalues, so this eigenvalue converges to infinity when you've got perfectly linearly related covariates. Okay, so all we're assuming is you can have correlation between covariates, but don't let them become identical in the limit. Right, so all we're assuming is this inverse is always going to exist, and that eigenvalue is not going to
We divide by n, and then raise it by.
Yeah.
So we want the eigenvalue to be equal.
Yeah, but I mean, if you look at exponential vector ran, typically for randomly generated design matrices, that would look like the sample covariance matrix, or it would converge. Its eigenvalues converge in general. I can't remember. I think it's like the Marchand question result.
Yeah.
I think that says that will essentially converge from randomly generated design.
And it's -1 with permutation.
Yeah, so again, that also pretty much holds for. If you look at the expression for C inverse, you can show that it looks. If you take randomly generated design matrices, again, it will converge to something non-zero. Yeah.
And then you
You get consistency in L2 norm. So, yeah. Okay. So the predictions are a little bit different. So for the predictions, we have x beta tilde star, which is our estimator, minus x beta star, which is our true value. If you scale the L2 norm by root n this time because it's a vector in R to the n, what you actually get is convergence to this constant on the right. And this constant depends on the Frobenius norm of Px, which is the projection matrix under the common span of x, and gamma, which was our diagonal matrix consisting of the variances of the response. Yeah. So really what to take away from this is that when P over N decays to 0, that norm scaled by root N goes to 0 as well, and you've got consistent predictions. If P over N doesn't decay to 0, then our predictions actually converge to a constant. And this is because our estimator is quite noisy. So the minute we apply OLS, what we get is a p-dimensional vector that tends to have p non-zero estimated values. Whereas typically something like a penalized logistic regression produces a sparse estimate, so it has a lot of zero values. So whilst our estimator accumulates a lot of error through those noise terms, other approaches don't because they're sparse. But this isn't too worrying, mainly because we mentioned at the start that there's already methods available for forming consistent predictions, so we don't really need another one for that. All we wanted was something that estimated the individual entries, something that could be used for variable selection, and our method does do that. So if you're given a data set, binary data set, and you want to form predictions, don't use our method, use something like a penalized logistic regression. But if you're interested in variable selection, then our method might be better.
Sorry, why that?
Because it converges to a constant, it doesn't converge to 0.
Yeah.
Yeah. Okay, so we've talked about our results, and we haven't really said much about how you can estimate eta hat beyond use something like a penalized logistic regression. So just to give a few details, the reason penalized logistic regression works well is because it exists even in cases where the MLE doesn't, right? So you can use our method in cases where the MLE does not exist. And all you have to do is, instead of maximizing the log likelihood, you minimize the negative log likelihood plus a penalty function, right? And there are already various results that say, as long as beta star is sparse, so it contains a few non-zero entries, that consistent predictions. So you can use it in our method. An alternative approach is a singular value decomposition. So the idea behind this is that one of the issues with maximum likelihood estimation is that when P is large relative to N, MLEs don't tend to exist. So the idea of singular value decomposition is just to reduce the dimension. Instead of performing maximum likelihood using the full set of covariates, you might just use the main left singular vectors of X. And then what you need is, as long as that signal X beta star is contained in those left singular vectors, then what you would get is consistent predictions. Yeah. So one thing to point out is that our method, it had fairly weak assumptions up until this point, and then here we introduce these assumptions of sparsity. But one good thing about it is that you can assume different forms of sparsity, right? If you believe beta star is sparse, then something like a penalized logistic regression is good. If you believe that it's sparse in terms of the number of components that are important, then you can use this approach instead. So it's quite adaptable. Another interesting case is the case where the MLE exists. And whilst this may not be practically very useful, it does provide an interesting relationship between our approach and maximum likelihood estimation. And the reason is, if you take the MLE, call it beta hat star, and you estimate beta using the MLE, so take beta hat equal to X beta hat star, and then correct the least squares estimator, right? And what you get is the MLE again, right? So not very practically useful, as we've taken the MLE, corrected the OLS estimator, and come out with the MLE again. But in terms of the link between our approach and maximum likelihood estimation, it's quite interesting, because all we've done to extend maximum likelihood estimation to cases where the MLE doesn't exist is changed our estimate of beta, right? So we've just changed it to something that does exist. So it's quite natural. Okay, so those were the main results. We can also look at the numerical performance. So we can see how our performance, our estimator behaves in practice. And we're going to take the limiting setting where P and N both go to infinity, this time keeping the ratio P over N fixed. And this is quite popular. Like Sir and Candace do this in, I think, both of their papers relating to logistic regression. And we're going to take various values of N and various values of kappa, or 2 values of kappa. Yeah. Then we generate our covariates from a multivariate normal distribution, where the correlation between covariates is just going to be 0.5 for everything. And then our response is going to be generated from a logistic regression model, where the unknown parameter beta star is going to have 5 non-zero entries set at 0.9, and the remaining entries are going to be 0. So our beta star is relatively sparse. Yeah. So for this, we repeat in 500 repetitions, we keep the design matrix fixed, generate 500 response vectors. Yeah. For each response vector, we compute our least squares estimator, and then we correct it using various estimators of eta. Yeah. So you can correct it, for example, the first one is going to just use the true value of eta to correct the least squares estimator. And that we're going to call the Oracle version because it's not very, you can't use it in practice in most cases, but it does serve as a reference point. We can also estimate eta using various penalized logistic regressions. So that's ridge, the SCAD and MCP that we use. And then we also use the singular value decomposition of X to estimate eta. So that's 6 different estimators based on our approach. And then we record the estimated signal strength for a null variable, for a signal variable. We look at the composite estimation error in terms of the L2 norm, and we also look at the prediction error. So here are our results. What you can see are the estimated, so the average estimated signal strengths for all of our estimators. In black, you've got the Oracle one, so that's not the one that's available. That's just the reference point where you plug in the true value of eta. And then the colors are described on the bottom. But on the left, you've got this case kappa is 0.1, so P over N is 0.1. And on the right, you've got P over N is 0.5. So P is larger on the right. And from the first plot, you've got the average estimated signal strength for a null variable. You can have a look. All of our estimators characterize that signal strength quite well. They're all quite close to 0 on average. You can also look at the estimated signal strength for a signal variable. So I've marked in the dash line here and also on the other one, the true signal strength, which was 0.9. And as you can see, all of our approaches managed to identify that there was a signal in this variable. The Oracle version is very close to that signal, which shows that our method does have the potential to estimate it quite well. And if you look at the standard MCP, so orange and purple, you can see that for large enough sample sizes, they also estimated that signal quite well. Yeah. The lasso, ridge, and SUD tended to underestimate the signal. And the reason we think this is, at least for the lasso ridge, is, I'm not sure if you're aware of these methods, but they're just a form of penalized logistic regression. But these methods tend to shrink estimated values. So they shrink the magnitude of estimated values, and this is passed through to the predictions as well. So what you get is a trying to estimate it as well for us. But typically SCAD and MCP are known to be less biased, which is why you get better performance with them. So smaller in magnitude, they are always closer to 0. Yeah, because of the penalty. If you think that the lesser penalty is in B, yeah, or even the L2, whereas the standard MCP are flat for large enough values of the parameter vector, so there's no penalty, like choosing a certain value. You look, the lasso penalty, for example, looks like that, and the SCAD is flat, right? So if you've got a large value of the true parameter, a SCAD, a lasso penalty is going to shrink that because it's going to make that likelihood plus penalty term quite large, whereas the SCAD is less effective. Yeah, so this is good. This shows us that at least 2 of our approaches, SCAD and MCP, do estimate the signals quite well. The right-hand side is the same, it's just larger P, so it's more difficult usually. Yeah. No, it's just a little bit, for some of them it is, and then it takes a little bit longer for it to converge, which you'd expect. And it's, yeah, a little bit more noisy, I suppose. Yeah. I mean, it still performs well, but it's worse. Because our results are all asymptotic. So we have consistency when n goes to infinity.
So these results apply however
yes, but obviously in finite samples, how well you estimate eta is going to play a role. Yeah, so asymptotically, as long as eta converges, great, you're going to be there eventually. But obviously, n is infinite. Yeah. So here we have the composite estimation error. So this was the difference in our estimator and the true value in L2 norm. And as you can see, that decays to 0 for all estimators. That was what we said would happen. And then in the prediction error, we've got it converging to a constant, which is also what we have said would happen, because we said predictions only converge to 0 when P over N gets to 0. Whereas in our case, we've got P over N is equal to 0.1, or P over N is equal to 0.5. Yeah, no, so asymptotically, it didn't matter, but I suppose maybe if you look in finite samples based on this, it does seem to be even worse as kappa growth. Like the prediction error does seem to depend on kappa in some way. With kappa being larger, you get even worse predictions. But we didn't really look into that, if I'm honest. Difference in L2 norm between our estimator and the true value.
So the idea that it's the same for
Yeah, no, so
so
basically
the trend
it's
is the
going to
same.
0, which is what we wanted. Yeah. So we can also look at how well our test statistic performs. So if you recall, I defined these TIs to test whether individual entries of our vector were 0. And we looked at the type 1 error, power, and distribution of the p-values under the null hypothesis. So we just used, I mean, the only reason I use I and J is because J is signal, I is null. Yeah, so we just use the asymptotic normal distribution of TI to compute whether to accept, reject, and then look for type 1 error, power, and p-values. And if you look at the type 1 error, you've got everything is controlled roughly at the 0.05 level, which is the significance level that we chose. If you look again, it's standard SCP, so orange, purple, and black. They were the closest to 0.05, which is what you'd expect, because, I mean, from what we saw earlier, the other estimates were a bit more biased. Yeah. And then if you look at the power, for large enough sample sizes, that power is close to 1. So we get, for large enough sample sizes, we're accepting and rejecting in a good proportion of cases in the correct way.
Now it's no longer
So I think, are you looking at this?
no,
But
I did that.
they're still at the top here,
Oh, yeah.
and they're still at the top over there, blue and red. So blue
great.
and the blue again. Yeah.
Yeah, no, then it's the same thing.
Yeah. You might look at this and say, blue and red are rejecting less false nulls. They must be better. But the reason this is they tend to underestimate. They always tend to underestimate the signal. So they select less. They, in general, I think they would reject less hypotheses overall, irrespective of whether they're true or false.
So you start as when you n equal 100, and for n equal 100, you're already in the simplification, so you find that very good.
Yeah. Yeah. I mean, there's obviously a little bit more loose. Like, if you look at the previous one,
or even n equal 100.
yeah, because it was identifying the signal. In all cases, it was quite an obvious change between the null and the signal variables when you looked at the estimator. But then if you looked at the actual estimated values, we needed sample size to approximate them well.
But this means that even at size 1, n equal 100, it's already
It's decent, yeah,
like
yeah.
the distribution.
But I mean, we did consider a relatively simple case where all the correlations were 0.5 as well. So, yeah. But we decided to. We've also got the distribution of the p-values. So this is the ordered p-values plotted against their theoretical expectation. And on the top, you've got n is 100. On the bottom, you've got n is 1,000. And in all plots, you've got, they follow the line y equals x. So the asymptotic distribution does seem to be quite accurate, even in finite sample sizes. But obviously, it does improve as n gets larger. If you take the p-values are uniformly distributed under the null hypothesis. The ordered p-values, I think they also have a distribution. I'm tempted to say it might be beta. But there's a result, whatever the order of uniform random variables is. And then if you compare the values of the ordered p-values against that theoretical expectation, so if it is beta distributed, then the expected value of it. Yeah, and I think it's literally just going to be like, if the first p-value is like 1 over the number of p-values. Yeah, theoretical versus proof. Yeah. Roughly, yeah. Is that okay? Yeah. So we also looked at a couple of more difficult situations. So these are situations where other procedures tend to struggle to identify that signal accurately because you've got a lot of correlation among variables. So what we did is we set up 3 examples where other procedures struggle. So we hoped that ours would work, and it turns out it did. So in the first example, well, let me just say that in all examples we compared our approach, so our OLS estimator corrected by some estimate of eta, with a SCAD penalized logistic regression. And our choice of SCAD was simply because SCAD tends to be less biased than other approaches, so we hoped it would perform the best out of what's already available. And for ours, just to compare, we corrected our OLS estimator using SCAD as well. So we use SCAD to estimate eta and then plug that into our squares. In the first example, what we've got is highly correlated signal variables with a weak marginal correlation with the response. So this makes it quite hard to identify these signal variables. And we did this by using the exact same formulation as we had originally in terms of generating the data, but we changed sigma and signal strength. So this time variables 2 and 3 are going to be highly correlated with correlation 0.95, whereas they're going to have cancelling signal strengths of 2 and -2. And as you can see on the left plot, we've got the average estimated signal strength for both approaches. So in black, we've got SCAD penalized regression. In orange, you've got our approach. And this is just the estimated values for each index of beta star. And if you look at index 2 and 3, the SCAD really struggle to identify that signal, whereas our approach is actually quite close to the true values. Yeah. And the reason this is if you look at the distribution of estimated signal strengths for the second signal variable, so this was one that was weakly correlated with the response. When you look in black at SCAD, you can see that quite often SCAD set that estimated value to be 0 because it was weakly correlated with the response. Right? Whereas our approach characterized that signal, which I've marked in the dashed line, a lot better. Yeah. So what happens is SCAD, because the variable is weakly correlated with the response, it quite often says, right, this variable is not important, estimating signal strength 0. Our approach didn't do that. You can look at the distribution of estimated values, and you can see that they're quite close to that true value, or at least a lot better than SCAD anyway. Yeah.
So it thinks it's weakly correlated because the 2 things are absolutely correlated.
Yeah.
And so it doesn't seem to be true.
Yeah, exactly. So if you looked at, say, x2 and x3 were your covariates, you look 2 times x1 minus 2 times x2 minus 2 times x3, that's virtually 0, right? If these were perfectly correlated, it would certainly be 0. Yeah. Okay. So just for another example of a similar kind of thing, this time we've got highly correlated signal variable with a noise variable. So that's going to be variable 2 is the signal variable, variable 6 is the noise variable. And if you look at this plot here at 2 and 6, you've got a SCAD penalized regression tends to be more biased. And if you look at the estimated the distribution of estimated values, you can see that SCAD quite often set the estimated signal strength of that signal variable to be 0 again. And in these cases, what it would do is it would probably confuse the signal variable and the noise variable. So it would give the signal to that noise variable instead and say, like, this signal variable is not important. Right? Whereas our approach didn't put any weighting really at all on 0. It was a lot better. Yeah. And then just the final case, you've got 2 highly correlated signal variables, this time with equal signal strength. And again, our approach is a lot less biased. And the reason this is, if you look at the estimated signal strength, a SCAD penalized regression estimated the value to either be 0 or quite close to 4, right? So it took the full signal strength corresponding to variables 2 and 3, which was just 2 plus 2, 4. So 2 of these, 2, 4. And it would either assign it to one of the two variables, so one or the other. And that's why you're getting either 0 or 4. Whereas our approach characterized that 2 a lot better. So it was able to distinguish between these two variables.
Explain again the 0. I didn't quite understand what you were doing.
So if we did lots of repetitions where we computed the SCAD estimated value, right? And this is just the distribution of the estimated values for this second signal variable. Yeah, so in a lot of cases, it was estimated to be 0. And in a bunch of others, it was estimated to be close to 4. Whereas the true value was 2. So that's not very good. Yeah, probably, yeah. So essentially the 4 is, it's how good can I estimate that full signal strength corresponding to the two variables. And then whether or not it's 0 or close to 4 is, right, let me give it to this first variable or let me give it to that second one. Yeah. So that's pretty much everything. So just in summary, we developed a consistent and asymptotically normally distributed estimator. So of the individual entries of beta star, you could also do like low dimensional sums of entries of beta star. It would also work with that. And our results are valid in a high dimensional setting, as long as p is less than n, even in cases where the MNE does not exist, and under fairly weak conditions. So we haven't assumed anything about sparsity of the precision matrix. Even sparsity of the unknown parameter is relatively flexible. So this is good. And we've seen that our estimator is good at estimating individual entries of beta star compared to existing methods. I will just point out again that it was less good for performing predictions. So don't use it for predictions unless the overrun goes to 0. But again, this isn't worrying because you can use something else for predictions, whereas our approach was mainly for variable selection and performing inference on individual entries. So there is a little bit of room for future work. On the one hand, there's the possibility to extend to other distributions. And the reason you might want to do this is because the limitations of penalized regression or other approaches in terms of identifying important variables hold irrespective of the distribution in general. So you could use our approach to do that a little bit better. And this basically just says that the methods are quite general. So you should be able to extend it at least to some other distributions. And I can go through the details if you're interested, but otherwise I'll let it. So sorry, what you said? So something where the distribution is not known. I mean, you specify the wrong distribution.
Yeah.
Yeah. So I haven't really thought about that. I don't know to what extent you need to have that true distribution, but I imagine it would, to the extent that how well does OLS work in the case of misspecified models would certainly probably play a role in our estimator. That would probably be the most driving, the biggest force in terms of how well our estimator behaves. Just another thought, which was just quite an interesting observation, is that there's actually quite a nice relationship between the logistic regression model and the normal theory linear model, in that if you take data from a logistic regression model, you apply these squares, what you get is actually an estimate that's very close to a multiple of the unknown logistic regression parameter. So if you apply these squares, you're going to get something, an estimator that has the relative sizes of the individual entries is going to be very close to that of beta star. Right? And our intuition for why this might be is based on this relationship that we had at the start. So the least squares estimator close to beta naught is going to be a linear multiple of beta star plus an error term. So our belief is that that error term goes to 0, but we haven't really been able to show it yet. And another question is, whilst this is an interesting relationship, it would be good if it's actually useful for something. So if anybody has any ideas, also really willing to hear. But yeah, I was just quite curious, and people seem to be quite surprised by that, because you don't expect these two models to be linked in that way. So that's everything really that I've been working on. Thank you very much for listening.